Solutions, and we talked about some concentration units. We talked about really molarity, which again is our moles per liter. As we talked about, you can think of this really as a sort of formula and that you could rearrange, and we do oftentimes solve for all three of these things. So once again, if you do want liters, that is going to be your moles divided by molarity. If you want moles, which again is a very common calculation, you do want your liters times molarity. Remember that you do need to convert your volume to liters for the units to properly cancel out, because really molarity is moles per liter. Otherwise, again, you will be off probably by a factor of 1,000 if you have milliliters. In addition here, when you are doing problems, also, as we talked about, it's a very good idea to get rid of the big M. And that does mean that there's 4.5 moles per 1 liter of sodium chloride. And once again, by sort of doing that and getting rid of the big M, you're able to see both units. So you can see where the moles are, you can see where the liters are. And as I mentioned many times, I think what's very common when people don't do that is they have no idea about the liters part or the volume part and sort of where it's at. I think we finished up last time talking about dilution. And dilution is really when we add more solvent to our solution. And again, in a lot of cases, that may be water, but not always water. And really, the result of a dilution is we do see the molarity go down. And again, the reason we see the molarity go down is because it is moles of solute divided by liters of solution is what molarity is equal to. And the solution is the solute and the solvent. And by adding more solvent, what we're doing is basically adding more to the denominator there, making that a larger number. And the result of that is, again, our molarity will go down. Most commonly used equation for dilution is really M1V1 is equal to M2V2. This is usually before the dilution. The more concentrated stuff, this is usually after the dilution. And that is obviously your more diluted situation. The M's there are molarity, the V's there are volume. And this is the one equation where you can use to leave the volume in milliliters. As long as it's milliliters on both sides, everything will cancel out okay. You could also, again, convert it to liters, and it'll be liters on both sides. But once again, if you are using just molarity and volume separate from a dilution problem, you should always convert it to liters so that you're in the right units. As I think we also talked about, if you do multiply milliliters times molarity, you get millimoles, not moles. So if you think you're getting moles when you do that, you're going to be off by a factor of 1,000. So it's really important to make sure you do that conversion. And again, you could also do the conversion to liters here using this equation, and it will come out okay. Typically speaking, V1 is how much of the more concentrated solution we need. V2 is our kind of final volume that we're trying to make. And a lot of times, if you're looking for how much water you need to add, you can subtract those two values, V2 from V1. And a lot of times that will give you the amount of solvent that you need to add to do that dilution. A more generic version of this is C1V1 is equal to the same formula. C here just stands for generic concentration. So it really could be any type of concentration unit you want. It could be molarity. It could be some of those other ones that we saw, like percent mass, percent mass volume, those type of concentration units. So as long as the concentration unit is the same on both sides, you really could use this. This equation should only be used with a dilution. You may be tempted to try to use it with some stoichiometry type problems, and you may get lucky every so often, but you really shouldn't use this with stoichiometry problems or titration problems like we did the other day in lab, because it's only works for a specific type of titration where the stoichiometry is 1-to-1. So if it's not 1-to-1, you will get it wrong because you will not have the right mole-to-mole relationship. So use this one strictly for only dilutions. If it's, again, a solution stoichiometry, we're going to talk a little bit more about here today. Use stoichiometry and not just plug into this equation. Any questions on any of that stuff there? All right, so I think we laid up here. I don't think we did this example, so let's do this one. What volume of 19 molar sodium hydroxide is needed to prepare 1 liter of a 0.15 molar solution of sodium hydroxide? I'm gonna pass this around. Just print your name legibly would be great, so I can at least read it. Okay, so let's take a look. So we essentially have a bottle here of a more concentrated 19 molar solution. We eventually here want to make a solution that has a volume of 1 liter, which is like 1,000 milliliters, and has a molarity of 0.15 molar. So this is definitely a dilution here. This is basically M1. This is basically M2 and V2. So obviously here V1, I'll get my numbers right, V1 there, is what we're missing. So we can use our M1 V1 equals M2 V2. Again, going to send our M1 to the other side. Going to give us V1 M2 V2 divided by M1. Again, in this case, unit-wise, we can leave it in milliliters, or you can leave it in liters. And in this case, we will leave it in liters. So we'll take 0.15 molar. We will have 1 liter. We're going to divide it by our 19 molar. So here the units of molarity will cancel, and that's going to get us something in the ballpark here of 0.0079 liters, or that's roughly 7.9 milliliters. First off, any questions on the calculation? Now, what that number represents is you would go to your more concentrated bottle and you would toss in there, we'll go with milliliters in this case, 7.9 milliliters basically of it. We want a total volume of 1,000 milliliters. So should I add just 1,000 milliliters of water in this case? I should not, right? Because now we're at 1,007, which is too much. So to figure out how much water, as we were talking about, I think the other day, in this case, the volume of water would actually be V2 minus V1. I'll just do it in milliliters. So we want 1,000 milliliters minus our 7.9 milliliters. Roughly, we would need about 992.1 milliliters of water would need to go with that. So after I would put my 7.9 milliliters of the more concentrated solution in there, I would top it off with, what I got there, 992.1 milliliters of water. At that point, I will have a total volume of 1,000 milliliters or 1 liter. And afterwards, I would mix it up. And that solution then should have a molarity of 0.15 molar. So sometimes people, again, mistakenly, when they're asked that question of how much water to add, which is a very common question is asked in dilution sort of problems, is they just go, oh, you just add the total volume there of water. And again, that throws your total volume off in that case. Any questions on that one? Okay, so taking a look at another one here. What volume of water is needed to prepare 500 milliliters of a 0.2? Okay, so on this one, same sort of situation. Here we got a bottle of 5 molar sitting here. Obviously, it's calcium nitrate and calcium nitrate, which means no reaction. We're just going to dilute it. We're shooting for a volume of 500 milliliters and a molarity here of 0.25 molar. Once again, this could be our M1 and our 2s. So once again, here we do not have our V1. So M1 V1 equals M2 V2. Dividing this to the other side gives us our V1 is M2 V2 divided by M1. Again, in this case, if you want to convert it to liters, you can, or you can leave it in milliliters, which is what I'm going to do. Obviously, though, if you did convert it to liters, your answer would be in liters. And in this case, my answer is going to be in milliliters. Once again, if you are using this formula, it works out okay. And the reason it works out okay is those molarities cancel. And now you're back to milliliters. So it's okay in that case. So we got 0.25 times 500 divided by 5 gets us roughly here about Okay, so it would be 25.0 milliliters in this case. And once again, that is how much we would take out of our starting guy. So the question, though, did want to know how much water that we need. So once again, here to figure out how much water we need to subtract our two volumes. So if we took our V2 minus V1 in this case, we're going to end up with 500 milliliters. We already added 25 milliliters, so 475 milliliters of water would be needed in this case. So again, we top it off with 475 milliliters of water. And now we can mix it. That gives us our total volume, and we would have our molarity of 0.25. Any questions on dilution? Yeah. Yeah. I got, okay. Yeah. Other questions? All right, questions on dilution. So I would say pretty simple formula, pretty simple calculation, but a lot of times people do miss the answer because they do ask for the amount of water or solvent a lot of times. So people just give like the answer as, in this case, like 25 or something like that. So make sure you do read the question correctly and you're answering exactly what they're asking. Any questions on dilutions? Okay, then we're going to talk about solution stoichiometry, which we did really some titration type problems and stuff last time, but stoichiometry involving solutions, not surprisingly enough, is pretty much like all other stoichiometry problems. So you will have either basic stoichiometry problems or limiting reagent type problems. So if it's a basic problem, you really do just follow the same steps that we talked about. You balance the equation, you convert things to moles. And if it happens to be a limiting reagent problem, right about there, you should do your limiting reagent calculation to figure out what is the limiting reagent. A reminder that that does involve a calculation, is not just the smallest number of moles. So you do have to do a calculation to figure out the limiting reagent. Can't just look at the moles and go, that one's smaller, it's going to be the smallest. So it does require some type of calculation. And then you will calculate the moles and convert those moles to something else using stoichiometry. The difference is a lot of times is how we get our moles. So that's going to, a lot of times in solution stoichiometry, be liters times molarity. And again, that would basically be our moles per liter, is very commonly how we get to our moles. Also, a lot of times it can just be a basic stoichiometry problem through this point. And at the end here, we could use something like molarity to figure out the moles and the volume, to figure out the molarity of a substance. If we have the molarity of a substance, we could use the moles to figure out the volume. So sometimes liters is figured out at the end. So a lot of times you may use at the beginning of the calculation molarity and volume to get the moles, and at the end, a lot of times you'll either be going into the molarity formula there to calculate molarity, or use the molarity and the moles to get to the liters. So those are two common sort of endings. Again, the middle part really kind of the same, regardless of what it is. So let's take a look at one here together and see what we come up with here. We want to calculate the mass of solid sodium sulfate that must be added to 250 milliliters of a 0.2 molar solution of barium nitrate to precipitate out all the barium ions in the form of barium sulfate. Calculate the mass of barium sulfate that is formed. So we got to start with the formula here. So we want to add sodium sulfate. So sodium is +1 and sulfate is -2, which means we should have something like this, a little Na2SO4. We're going to add that to barium nitrate. Barium is +2. Nitrate is -1, which means we end up with something like this. This, at this point, you should recognize as a double displacement reaction, which means our two positive guys are going to switch partners. And as we've talked about many times, you want to make sure that you get the right formulas first. So don't worry about the balancing. You want to get the right formulas. So that means when the sodium comes together with the nitrate, sodium is +1 and nitrate is -1, which means you should end up with a little NaNO3. And barium, which is +2, and sulfate, which is -2, when they come together, you just need one of those, and that would be your solid in this case. Any questions on how we get to the formula here? Once we have the proper formulas down, now we really can't do the stoichiometry part here until we actually balance it. So it is not balanced in this case. So maybe like a 2 right about there. And at that point, I think we are good. So I think we just need a 2 right about there. Any questions on that there? All right, so now we got the equation, which is always the first part of any stoichiometry problem. We want to kind of see what they gave us. So they gave us that we are going to be using 250 milliliters of 0.2 molar barium nitrate. And we want to know how much sodium sulfate. So we want to know this guy. We actually want to know the mass of it. And we also want to know at the end the mass of this guy that is formed. So at this point, we can do our second step of stoichiometry, which is convert to moles. And by the way, this is obviously not a limiting reagent problem, since the only thing that we could get is, in this case, barium nitrate in terms of moles. So obviously we can't get the other guy because that's what we're looking for. So it's just a basic stoichiometry problem. So instead of using grams to moles, we're going to use the volume and the molarity here. Remember that we do need to convert our volume into liters because we're going to use it with molarity. So that is 1,000 milliliters is a liter. And that will get us 0.2500 liters of barium nitrate. So I'm going to use that 0.2500 liters. I'm also going to get rid of this big M and turn it into moles per liter so I can see both of the units there. And that means that up on top is the 0.2 moles and liter of barium nitrate. And that will get me 0.25 divided by, not divided, 0.25 times 0.2. And give me 0.05 moles of barium nitrate. So this is basically step number 1. This is step number 2. Any questions so far? Oh, really, we could go step number 3 here. I'm just going to go up on top to use a little bit more room here. All right, now we're looking for really 2 things. So I'm going to first go this way and figure out how many grams of my sodium sulfate. It really doesn't matter. You could also have went this way first. So it's whichever way you kind of want to go first. It doesn't really matter. So in this case, between sodium sulfate, it is 1 mole of sodium sulfate gives me 1 mole of barium nitrate. So that makes it pretty easy to continue on. So we're going to go our 0.05 moles of barium nitrate. We're going to do the stoichiometry from the equation, which is a 1 mole of barium nitrate will give me 1 mole of my sodium sulfate. At this point, if I stop right at this point, I am in moles of sodium sulfate, which is close to what I want, but I do want grams of it. So I do need the molar mass from the periodic table to do that. So I'm going to calculate the molar mass of sodium sulfate. And that means that I have for sodium sulfate here, I got 2 times 2299, which is our sodium's molar mass from the periodic table, 3207, which is our sulfur. And we got go above 4 times 16. for our oxygen. So if we add all that together there, 2 times 2299 plus 3207 plus 4 times 16 gets us 142.1. So I'm going to use that as my conversion factor here. 142.1 grams per mole of sodium sulfate, which is what we get down here. And that will get rid of my moles and leave me grams. And it will tell me in this case here, we need about 7.11 grams of sodium sulfate would need to be added to that 250 milliliters of that 0.2 molar solution. Any questions on that one there? Now I'm going to continue on and answer the second part of the question, which was how much of that product we made. So to do that, I need the mole to mole relationship between our barium nitrate and our barium sulfate, which happens to be 1-to-1 as well, so that ain't bad. So 1 mole of our barium nitrate will give us 1 mole of our barium sulfate. So I can just pick up once again from here, and we'll go with our 0.05 moles of barium nitrate. We will use our mole to mole relationship just like we did above. 1 mole of barium nitrate will give me 1 mole of barium sulfate. Just like above there, we're looking for how many grams. So I do need to go back to the periodic table and figure out the molar mass of our barium sulfate. So barium sulfate in this case, barium is about 137.3. 137.3. Sulfur is 3207. And we have 4 oxygens there. And that's going to get us 137.3 plus 3207 plus 4 times 16. About 233.4. So we'll use that as our last conversion to go from moles to grams. So a mole of barium sulfate is 233.4 grams. The moles will cancel, leaving us grams, and we will end up with here 11.7 grams of barium sulfate. By the way, since that is a product, that would be our theoretical yield in this case, would be our barium sulfate in this case. So once again, hopefully you can see it is the same 4 steps in this basic problem. We did the first 2. This is the 3rd and the 4th for that calculation. That's the 3rd and the 4th step there for that calculation. In this case, we actually used the molarity and the volume up front, and we just did a basic stoichiometry problem at the end using at the end there to figure out how many grams. But just as easily, you know, you could have figured out molarity or volume if it was some type of solution you were looking at. Any questions on any of those steps there? All right, so why don't you try one then here? Maybe if there's one. All right, calculate the mass of calcium carbonate that would form when 25 milliliters of calcium nitrate reacts with 20 milliliters of sodium carbonate. I'll give you some numbers that might be helpful. Calcium 4008, carbon 12.01, oxygen 16. All right, so go through the steps, figure out what you need to do. I would say start with an equation would be good, probably, yeah, good idea. So once again here, obviously, we're looking for the mass of calcium carbonate that forms when we're mixing 2 solutions together, calcium nitrate and sodium carbonate. So obviously it's a stoichiometry problem. So we need to start with the equation. So we're going to take some calcium nitrate here, which would be aqueous since there's nitrate involved, and sodium carbonate, which would also be aqueous. We also know that because they said that they were solutions. Once again, you should see the double displacement sort of setup happening here. So our calcium is going to go with our carbonate, and our sodium is going to go with our nitrate. Once again, like we did on the last one, we want to put them together correctly. So calcium is +2, carbonate's -2, which means we will end up with CaCO3, and that's going to be our solid. And sodium is +1, and nitrate is -1, which gives us NaNO3, which would be aqueous. Once again, it does not give us Na2NO3 too. Yeah, so again, you want to put the right formulas first. Any questions on that there? Now that we have the right formulas, like normal, none of the stoichiometry part will work unless we do some balancing. And in this case, perhaps I think we need some 2s maybe. Let's see. I think a 2 right there. And at that point, perhaps we're good, I think, in this particular case. So we are good in this case. So in this problem, they did give us that we're going to take 25 milliliters of this guy, and it has a molarity of 0.1, and I'm going to get rid of the big M and convert it into moles per liter. And for our sodium carbonate here, gives us 20 milliliters, and I'm also going to convert it into moles per liter. So what you should recognize, hopefully at this point, is it is a limiting reagent problem because you're given enough information about both of the reactants to get the moles, right? So we have the volume and we have the molarity, which means we can get the moles of each reactant. That means somewhere along the way, we do need to do the calculation to figure out which one is the limiting reagent. Any questions on that there? Second step's still going to be the same. We just really need to convert those into moles. So here we do, again, need to convert our milliliters into liters. So we'll take our, basically, I don't know how many grams of this guy. We're going to take our 0.025 liters, which is what you get here when you convert it into milliliters divided by 1,000. We're going to take our molarity here of our calcium nitrate. And that will give us, in terms of our moles, 0.0250 times 0.1. Gets us 0.0025 moles of calcium nitrate. We're going to do the same thing here. So we're going to convert this guy again into liters. So basically 1,000 milliliters is a liter, 0.0200 liters. So we'll take that as 0.0200 liters, times it by its molarity, 0.15 moles per liter. Liters here will cancel. Going to give us 0.02 times 0.150. 0.003 moles of our sodium carbonate in this case. So remember that this is the starting amount of that guy. This is the starting amount of this guy. And we talked about a couple different ways you can figure out the limiting reagent, but you do need to do the calculation. So what I'm going to figure out is if I want to use up all my calcium nitrate, how many moles of the sodium carbonate I would need to put in there. So this is my calculation to figure out the limiting reagent. So if I take the moles of my calcium nitrate, and I do the mole-to-mole relationship between calcium nitrate and my sodium carbonate, it is a 1 mole calcium nitrate to 1 mole of sodium carbonate, tells me that I need 0.0025 moles of sodium carbonate is needed. First off, any questions on that calculation? This is to determine the limiting reagent. When we have that number, we now want to compare it to, in this case, how much we're starting with. And do I have enough in this case of the sodium carbonate? I do. I only need 0.0025. I got 0.003. So I have enough, which means that our sodium carbonate would be our excess reagent and our calcium nitrate would be our limiting reagent. Any questions on that? So you need to do some type of calculation like that. The alternative to that calculation is you figure out how many moles each one would produce of your product, and whichever one produced the least amount would be your answer and your limiting reagent. So again, there's a couple different ways you could do it. Now that I know which one's my limiting reagent, I now can finish up the problem. I'm going to take my starting amount of my limiting reagent. And this is my limiting reagent. And I'm going to do the mole to mole relationship from the equation between my limiting reagent and the product in this case. And obviously, as you know, they're not always going to be 1-to-1, just happens to be in these few examples here. That's going to tell me that if I stop right there, that would tell me how many moles of my calcium carbonate I would produce. But we are looking for grams. So I'm going to need the molar mass here to finish up the calculation. So calcium is 4008. Carbon is 12.01. And we got 3 oxygens there in our product. And that is for calcium carbonate. And that will give us 4008 plus 12.01 plus 3 times 16, about 100.1 grams per mole. We will use that to finish out the calculation here. 1 mole of calcium carbonate will give us 100.1 grams of it. The moles will cancel, the moles there will cancel. That's going to get us 101.1 times 0.0025. And give us here 0.253 grams of calcium carbonate would be produced in this case. And this again would be a theoretical yield. 3 sig figs, because pretty much everybody's 3 sig figs there in that problem, and we pretty much multiplied and divided all the way through, so end up with about 3 sig figs at the end. Question on that? So once again, it really is the same steps, again with our calculation to figure out the limiting reagent, balanced equation, convert to moles, our limiting reagent calculation, and then our third step, mole to mole relationship and moles to grams in this case. So once again, really the same 4 steps, just using obviously volume and molarity. And as you can see here, can still have a limiting reagent situation that occurs. So you always want to kind of think about that as you're doing problems, especially stoichiometry problems. You know, is it a basic problem? Is it a limiting reagent type problem? Any questions on any of that there? Yeah. We do not, because we're not doing a dilution in this case or anything. So if you're talking about what we did previously, we subtracted the volume previously because we were just doing a dilution, which means we were just adding the water. And that's what we were trying to figure out, is basically how much water. This is actually a chemical reaction that's taking place that's going to produce this solid precipitate. So again, this is really more of a stoichiometry problem than the previous one. Yeah. And you just always go into a smaller amount of things. Yeah, so it won't always be, obviously, it won't always be a 1-to-1 relationship, but in that case, obviously, because it's a 1-to-1, you would need the same numbers of each of them basically to use them up in that case, yeah. But definitely if it's not 1-to-1, you gotta, and even with 1-to-1, you should always show the calculation. You gotta always show it, yeah. But even without a 1-to-1, sometimes people think that's, you know, how you figure it out. It's just like whichever one's the smallest, but it is really based on stoichiometry. Other questions? All right, so this is one type of solution stoichiometry problem. Let's talk about another type, which is basically what we kind of did in last week's lab when we did titrations. And when we did titrations, for example, those are acid-base neutralization reactions. And as you reach the equivalence point in a titration, you basically hit the point where all the acid and all the base basically neutralize each other. You've added exactly the same amount, for example, of base to acid. So when you did those titrations and it turned pink, even with just one drop, super dark pink maybe, at that point, you basically hit the point where, in our example there, you added enough moles of base to completely use up all the moles of acid that you started with. Overall, what is happening when we do an acid-base neutralization reaction, and especially pretty much a strong acid and strong base, if you go through our total ionic equation, net ionic equation, pretty much what is happening is that formation of water, like we talked about when we talked about different types of reactions. And again, that's one of the reasons why a reaction takes place, right, is that formation of water. So ultimately what we're doing here is forming water, and we can still do solution stoichiometry to figure out things, much like the experiment, you know, the molarity of an unknown solution. We could also figure out how many grams as well. So when we do a titration, it's a common solution stoichiometry problem where we're basically figuring out, you know, how much of that acid or base that we had, the molarity of that unknown solution. Solution stoichiometry, much like the one previous problem we just did, also includes, you know, kind of like that experiment we did earlier on with the yellow solid, right? That was basically solution stoichiometry in that particular case as well. So let's take a look at one here together. So if we did this sort of neutralization, which is sort of like the word sometimes used for like a titration type problem, we take nitric acid, how much volume of nitric acid is needed to neutralize potassium hydroxide. So it is a stoichiometry problem. So we're going to start with our reaction, which is our nitric acid and our potassium hydroxide. Once again, you could recognize this as a double displacement reaction. You hopefully should recognize this as an acid and base reaction, which means if you do recognize it as an acid-base reaction, you should always make water, and that's the H from the acid and the OH coming together for the base to make water. And then our salt, which is the other two guys coming together, which gives us KNO3. So that's our water and our salt, which again is very commonly made when you take an acid and base reaction. It is obviously under that big umbrella of double displacement reactions like we were just doing previously. So basically our two positive guys switch partners in this case. If we look at what we're trying to find in this case, we want to make sure it's balanced. So in this case, it actually is balanced, I believe. So we're good to go on that. What we're looking for here is the volume of our nitric acid. We do have the molarity, which once again, I'm going to convert into moles per liter. For our KOH, we have 45 milliliters, and we also have the molarity here of our KOH. So first off, is this a limiting reagent problem? It is not, right? We could only get moles, obviously, of our KOH, and we're also looking for the other reactant, so it's definitely not a limiting reagent type problem. But we can definitely get to moles for these guys, and that's really where we want to start in this case. So we will, again, have to convert our milliliters into liters, so we have the correct units. So again, we're going to divide by 1,000, 0.045 liters. So we'll start with that, 0.045 liters. This is, again, basically converting to moles. So we're going to use the molarity of our KOH. The liters here will cancel, and that will get us 0.045 times 0.550. To give us 0.0248 moles of KOH. Once again, here we're not interested in KOH, we're interested in nitric acid. So we need to go from KOH to nitric acid, which in this case, again, is a 1-to-1 relationship. So 1 mole of nitric acid will give us 1 mole of KOH. So that is the next thing that we'd want to do here. 1 mole of KOH gives us 1 mole of nitric acid. Moles of KOH will cancel, going to give us 0.0248 moles of nitric acid. That's important. Now, if I think about molarity for my nitric acid, I now have the molarity, and using stoichiometry, I now have the moles, which means I could rearrange this and solve for liters at this point. And that's really the purpose of the stoichiometry part here, is to figure out the moles of the acid that we need. Any questions on that there? So now we're going to rearrange it, and liters will equal moles divided by molarity. So I'm going to take my moles and I'm going to do a dimensional analysis way so that I can see all my units here. I'm going to divide by the molarity of the nitric acid, which is 0.15 moles per liter. So again, this is why we do want to get rid of the big M, so we can see both of those units, because a lot of times at this point, people have no idea about the volume or where it is or what they should be doing with that number. So here we could hopefully clearly see we should be dividing. And if we do that, 0.0248 divided by 0.150 will get us about 0.165 liters of nitric acid, which we maybe want to convert it maybe into 165 milliliters of nitric acid as well. You could actually leave it in either one, because it didn't ask for a specific unit in this particular case. Any questions on that? So this is really like a titration problem, very common sort of problem. Still the same steps for basic stoichiometry, balanced equation, convert to moles, mole to mole relationship, and here at the end, convert those moles into some other unit, in this case using molarity at the end to figure out volume, which is again a very common sort of calculation. Any questions on any part of that there? All right, so why don't you try one here, maybe? See what we got going on. All right, what volume of sodium hydroxide is required to react with 125 milliliters of 0.5 molar sulfuric acid? So give it a go. Again, I would recommend perhaps an equation to start with. Good. Okay, so let's take a look. So once again, we're going to do a reaction. So sulfuric acid is H2SO4. Sodium hydroxide is NaOH. Once again, this is an acid-base reaction or a double displacement reaction, however you want to look at it. Basically, the H and the OH will come together again to make our water. Our sodium and our sulfate will come together. Once again, it's important to put this together correctly. So sodium is +1, sulfate is -2, which means when we put them together, we actually should end up with an Na2SO4. So again, important to make sure you get those right formulas down. Now that we have it, we also want to make sure that the equation there is balanced. So I believe we're going to need some numbers here. So we'll go with a maybe a 2 there and maybe a 2 there. I think at that point we should be balanced. Any questions on getting the equation? At this point, we're looking for, I guess it would help to have some molarity for our sodium hydroxide, huh? I suppose that would probably help. I won't put a number in there, that would probably help. So we'll just go with that one right there. We got 125 milliliters and 0.5 molar. In this case, obviously you got to erase somewhere, 0.25 molar sodium sulfuric acid in this case, and we are looking for a volume. All right, at this point, we can only obviously get moles from this guy, and we are looking for something about the other reactant, which means it is not a linear reagent problem, it's just a basic stoichiometry problem. So we will convert to moles. So we're going to take our 125 milliliters We're going to divide it into liters, so we're in the correct units. And that'll give us 0.125 liters of our sodium hydroxide. We're going to convert our molarity into moles per liter, and we're going to multiply by it. That will get rid of our liters of sodium hydroxide, and that will get us 0.125 times 0.5. It says 0.0625 moles of sodium hydroxide. Once again, here we're interested in sulfuric acid. So from the equation, the relationship between these two is for every 2 moles of sodium hydroxide, we get 1 mole of sulfuric acid. So that is what we're going to do next. 2 moles of sodium hydroxide on the bottom, so they cancel. 1 mole of H2SO4 up on top. Going to get us divided by 2, basically. 0.0313 moles of sulfuric acid. Obviously, if you got up to this point, you really couldn't get the answer here because you're missing the molarity. So now that we put in a molarity there for our sulfuric acid, best you could have done with that maybe is molar mass to get how many grams. But in this case, now we do have molarity, so we'll use that. We'll use our moles. Now we can solve for volume. So liters will equal moles divided by molarity. So taking our moles, once again, getting rid of the big M and putting it as moles per liter. We do want the moles on the bottom so that they cancel. So 0.25 moles per liter of H2SO4. So we're basically dividing by the molarity like we see here. Our moles will cancel, and that will get us 0.0313 divided by 0.250. Going to give us 0.125 liters of sulfuric acid, or that's 125 milliliters of sulfuric acid would be needed to neutralize that. Yeah. We are trying to find sodium hydroxide, so I clearly did that whole thing backwards, and yes, thank you very much. So, it's a banner example, I think. Really, I think it's probably one of the nicest examples we've done earlier. So when we just see this, actually, we are looking for sodium hydroxide. All right, let's do a little fixing there. So H2SO4 and 2 of our sodium hydroxide. That looks better. Now we just need to fix some of our things down here. So obviously at this point, this would be our sulfuric acid. We obviously will need to flip our stoichiometry here. So that's moles of sulfuric acid, which means 1 mole of sulfuric acid, 2 moles of sodium hydroxide. And that's going to give us a different answer here. Here. All right, so let's see. So that will get us 0.0625 times 2 gives us 0.125 moles of sodium hydroxide, as the sulfuric acid will cancel. Then we'll take our 0.125 moles of sodium hydroxide. Sodium hydroxide there, and we'll divide it by 0.250. Looks like 0.5 liters of sodium hydroxide are 500 milliliters. Sorry about that. So be good to start with the right numbers, I suppose. Any questions on that when we use the right numbers there? All right, so clearly that's a sign we should stop. Yes, all right.